The Standard Model. Key areas covered today. Standard Model of fundamental particles and interactions. Evidence for subnuclear particles and the existence of antimatter. Fermions, the matter particles, consist of 6 quarks, up, down, top, bottom, strange and charms, and leptons, electrons, muon and tau, together with their neutrinos. What we will do today is explain and describe the subatomic particles that make up the Standard Model, state what is meant by antimatter, and define fermions, and state that they consist of quarks and leptons. First of all, let's revise the subatomic particles we're already aware of, the proton and neutron and electron. Let's examine their relative masses and their charges. The proton has a relative mass of 1, a charge of +1, and a symbol of P11. The one at the top is the atomic mass. The atomic mass is made up of the number of protons plus the number of neutrons. The number at the bottom is the atomic number, and that's made up of the number of protons. So when we look at the neutron, its mass is relatively the same as a proton, however it has no charge, and its symbol is 10. It's 10 because there are no protons, therefore the atomic number is equal to 0. However, there is 1 neutron, and therefore its atomic mass is 1. The electron is much smaller than the neutron and the proton, and we see that the electron most often is shown with a lowercase e, normally like this. Its mass is approximately 1 divided by 1,840th of the mass of a proton or a neutron, so much smaller. Its relative charge is -1. It has the same value of charge as a proton, however it is opposite. And its symbol is E0 -1. The -1 represents the absence of a proton. If we put a proton and an electron together, we make a neutron. You may remember from National 5 about beta radiation being fast-moving electrons coming from the nucleus of an atom. Beta radiation is formed when a neutron breaks up to form a proton and an electron. So what happens when we break everything down? Well, all matter is made up of elements. Elements are made up of atoms. Atoms have a central nucleus, and that central nucleus has protons and neutrons. But can we break the protons and neutrons down any further? Yes, we can. There's a link here which you'll be able to follow when you have a look at the PowerPoints, which are online, and that takes you to something called the particle adventure, which tells you a little bit more about subatomic particles further than the protons and neutrons. So what makes up protons and neutrons? Well, protons and neutrons, as found in the nucleus, can be broken down into smaller subatomic particles called fermions, matter particles. Fermions are part of the Standard Model of fundamental particles. Fundamental meaning they cannot be broken down any further. Again, there's a couple of links here that you'll be able to follow. These will take you to a little bit more information about, for example, the Large Hadron Collider and particle accelerators, which is what we use in order to try and find out a little bit more about how these particles came to form the matter that they do, and also find out what matter is made of. These subatomic particles are far too small to see and very difficult to isolate. So we have to build the particle accelerators in which they literally smash particles together. They smash particles together and then measure what is happening after that. So we're looking at examining the little pieces. And remember, those little pieces, some of the matter, also would have been transferred into energy. So we measure those small amounts of energy as well. So what is the Standard Model of fundamental particles? Well, basically, the physicists have developed a theory called the Standard Model, and it explains how all matter exists, what makes up the world, and how it's all held together. It's a pretty simple, however, it's a comprehensive theory that all of the hundreds of particles and all of the interactions happen between them. All the elements made up from the neutrons, protons, and electrons exist because of a certain set of blocks. So you can think of it in terms of a Lego model. You have a Lego model with lots and lots of different pieces, but you can make many, many different models from those basic pieces. The fermions are the matter particles, and they're made up of 6 quarks, up, down, top, bottom, charge, and strange, and then they interact with the leptons. Now we've got 6 leptons. The best well-known of those is the electron. However, we also have the muons and we have the tau, and they have other associated particles called neutrinos. We also have force carrier particles. Now, these are particles which carry a particular force, and there are 4 fundamental forces we'll look at later on. An example of this would be a photon, which you're very aware of from previous topics. Now, these force carrier particles, as opposed to the matter particles, are known as bosons. And we talk about bosons a little bit later on. You may have heard of the Higgs boson, for example, that was discovered at CERN in the Large Hadron Collider. Now, all known matter particles are made up of the quarks and the leptons, and they are known as fermions. The fermions interact with each other by exchanging the force carrier particles. And when the fermions interact with each other, they can go on to form the larger subatomic particles like the protons and the neutrons. However, with every yin, there is a yang. So for every type of matter particle we know, there also exists a corresponding antimatter particle, or we call it an antiparticle. Now, the only difference between an antiparticle and a particle is that they have the opposite charge. So they have exactly the same mass. To all intents and purposes, they look exactly the same. However, if one is positive, the other one is negative. For example, a proton is electrically positive, as we mentioned earlier on. However, an antiproton is electrically negative. Another example is an electron is electrically negative, but a positron is electrically positive. So many subatomic particles have been isolated and studied in the particle accelerators such as the Large Hadron Collider and CERN. The fermions have an antiparticle which has the same mass as opposite charge as we mentioned previously. And the examples we brought up was the electron with the negative charge and the antiparticle, the positron, which has a positive charge. All of the different antiparticles together are called antimatter. And when matter and antimatter come together, they cancel each other out and produce a large amount of energy. Again, there's another link which you can follow in the PowerPoint, which will be available on Teams. We have a look at a past paper question here. 3 students each make a statement about antiparticles. Statement number 1, an antiparticle has the same mass as its equivalent particle. Absolutely true. Statement number 2, an antiparticle has the same charge as its equivalent particle. Incorrect. By definition, an antiparticle has the opposite charge. Statement number 3, every elementary particle has a corresponding antiparticle. Absolutely true. So our correct statements are 1 and 3 only, which is C. Here's another past paper question. 2012 revised higher. An electron and another particle of identical mass pass through a uniform magnetic field. Their paths are shown in the diagram. The region of the magnetic field is in the center. We can see one path goes up, that's the path of the electron. The other path goes down. So they're going in opposite directions within the magnetic field. Now, this observation provides evidence for the existence of antimatter. So, what are the fermions? Well, the fermions, the matter particles, are made up of quarks and leptons. and then they're split into their particles and the antiparticles. The 6 quarks quite literally have very strange names. So first ones, the ones that we're most familiar with, are up and down. And it's the up and down quarks that go on to form our protons and neutrons. But you also have strange and charm and top and bottom. Now the strange and charm, top and bottom have the same charge as the up and down, however they become more massive. So top and bottom's more massive than up and down, and when they're more massive they tend to be very unstable. So you don't see them in everyday interactions. There are also 6 leptons which go along with the quarks. We have the electron and the electron neutrino, which has a much smaller mass than the electron. The muon and the muon neutrino, which again has a much smaller mass than the muon, and the tau neutrino, which again has a much smaller mass. Okay, so if we have a look at the first CFE specimen paper, we have this question. Student makes the following statements about an electron. Statement number 1, an electron is a boson. No, it's not, because it's not a force-mediating particle. Electron is a lepton. Yes, it is. Electron is a fermion. Yes, it is, because fermions are made up of quarks and made up of leptons. So which of these statements are true? That's 2 and 3 only, so that is E.